Welcome back. In the last lecture, we corrected a small imprecision about the row-reduced echelon form. We solved a bunch of linear equations, and we looked at row space, column space, as well as the determinant of a matrix and why to care about it. The determinant tells you precisely when the matrix is invertible. Although we won't use it, you can also recall that you actually have a formula for solving Ax equals b in terms of determinants. That's called the Cramer rule. Okay, if you're interested, you can look it up, but it's not very helpful in practice, so maybe it's not helpful in practice, but again, it's a useful theoretical formula to have for pure mathematics students for various reasons, which we won't get into now. Okay. Anyway, so far we have done. We've simply studied linear equations, how to solve them, etc. We have not studied the geometry of Rn. When we talk about geometry, we mean distances and angles, right? So all of this is encapsulated in the notion of a dot product of sorts. We won't call it a dot product, we'll call it by the more familiar term, inner product. Okay. So the standard dot product on Rn is defined as follows: A dot b, which we'll write as x y with brackets, is sum over I of xi yi. Recall that in R3, A vector dot b vector is a1 b1 plus a2 b2 plus a3 b3. This is simply a generalization of this definition to Rn, right? And x dot x, which is sum of xi square, in R3 this would have been, what would this be? This would simply be the length of the ray pointing from the origin to this vector, right? This is the Pythagoras theorem. Right? Here we define the length squared of a vector by this formula. This is a definition. Yeah? You need to define length somehow. This is how we do it. Okay? Okay, more generally, recall, more generally, we can define, recall that more generally, an inner product on a real vector space. This time, by the way, we have to deal with real or complex numbers. If you're familiar with more general fields, inner products don't make sense in them. It's written like this: it's a map from V cross V to R. It takes in two vectors, two vectors from V, and spits out a real number, and it satisfies a bunch of properties. It scales properly on each entry, right? It's also multilinear, meaning x1 plus x2 inner product y is x1y plus x2y. The x2 dot y likewise in the second one. In fact, xy, the inner product, is y dot x. So from this property we can see that it works this way as well. Okay. So it's linear in both entries and it's symmetric. Lastly, x dot x is greater than or equal to 0 with equality if and only if x is 0, right? This is if you have a real vector space. If you have a complex vector space, it's a bit more technical. Here, the inner product is again a map from V cross V to C. This time, though, alpha xy is alpha times xy, but x and alpha, the key point is x dot y is not y dot x, it's y dot x bar. So as a consequence, x comma alpha y is alpha bar xy. This property remains the same, and so does this. Okay, this is the only slight technical complication in a complex vector space. So on our end, the usual dot product functions as an example, On Cn, the correct example, the correct way to generalize this is not xi yi bar. Indeed, x comma x is sum of mod xi square, which is positive. Okay. Otherwise, this won't even be a real number, right, if I did not have the bar here. Okay. So recall that this is an inner product. Now, what can we do with inner products? As I said, the norm and norm associated to an inner product is defined as follows: norm x equals square root of x dot x. Okay. Now the point is, so in other words, this is the length of a vector of x. Now there is one very important inequality which we will use very often. It's very important for both pure mathematics as well as for more applied things, the Cauchy-Schwarz inequality. So the inner product of x and y is less than norm x times norm y, and equality holds if and only if y and x are linearly dependent, meaning one of them is a multiple of the other. Okay. Proving the Cauchy-Schwarz inequality, it's not trivial, it's not too difficult either, but it will take us too far afield. I'm assuming you've already seen the proof. This is motivated, so in R2, for example, A dot B is mod A mod B cos theta. Yeah. So mod of A dot B is obviously less than or equal to mod A mod B, and equality holds if and only if theta is 0, which means A and B point in the same direction, they are linearly dependent. Yeah. So it's a generalization of this observation, except you don't have this geometric cos theta business. In fact, cos theta is defined, the angle between vectors is defined using this. Okay, this is a definition in higher dimensions, right? Okay, now using this Cauchy-Schwarz inequality, we can prove that norm of x plus y is less than norm x plus norm y. This is the so-called triangle inequality. Yeah. Also, we see that this implies obviously that this is less than norm of x minus y plus y. Why? Because this is x minus y plus y. So using this observation, we also have the so-called reverse triangle inequality. Okay, this is called the reverse triangle inequality. All right. By the way, the notion of a norm makes more generally, as we will discuss in just a moment. But prior to that, we also define orthogonality of vectors of v and w. This is just a fancy name for saying v is perpendicular to w, right? So the definition is the inner product of v and w is 0, right? An orthonormal basis, of a vector space equipped with an inner product is a basis E1 etc. such that each of these has norm 1, that is why normal, and different things are perpendicular to each other, that is where the ortho comes from, for all I not equal to j. So, for example, on Rn with the usual inner product, the standard basis vectors form an orthonormal basis. Form an orthonormal basis. Yeah. Now, the point is, in any finite dimensional vector space, okay, so any basis in a finite dimensional vector space can be transformed into an orthonormal basis. So, every finite dimensional vector space with an inner product does have an orthonormal basis, and the procedure is called the Gram-Schmidt algorithm, which we won't get into. Okay. Please read it up, right, if, to recall what it is. Now, the point is, if you take two orthonormal finite ordered bases, I won't put a set sign here. Suppose these two are orthonormal bases. The change of basis matrix, what is the change of basis matrix? This is a linear combination of these Fi's. This is a linear combination of these Fi's and so on. We put these S's together, you get a matrix. The change of basis matrix between two orthonormal bases turns out to be orthogonal. Orthogonal. And in fact, it is if and only if. If this is an orthonormal basis and I change it by an orthogonal matrix, I get another orthonormal basis. And if I have two orthonormal bases, the change of basis matrix is orthogonal. Okay? That is why this is called an orthogonal matrix, precisely because it is used to change two orthonormal bases. This is in a real vector space. If you play the same game in a complex vector space, then the corresponding matrix will be unitary. Okay? Right. Okay, so that's the reason to care about orthogonal and unitary matrices. I mean, this requires proof, by the way. I'm not proving it. I'm just recalling these facts which you're supposed to know, right? Okay. So, more generally, we can define a norm on a vector space. So, suppose you have a vector space V, a norm is supposed to be, regardless of whether it's real or complex, this is supposed to be like the length of a vector, or perhaps the distance of the end point to the origin. Okay. So, more generally, what is a norm? A norm is simply a function from the vector space to R, and if you scale a vector, the length scales, where this is a scalar, it can be real or complex, yeah, and V is 0 if and only if the vector is itself 0, right. And lastly, you have the triangle inequality. So, this is the triangle inequality, right. Now, and what are examples of norms? The usual norm associated to an inner product, to a dot product, namely this one, that's defined to be this. And by the triangle inequality proven here, all the properties are met. Okay. This is sometimes, so in Rn or Cn, if you take the usual inner product, then the usual norm, the usual norm, that is this one, square root of mod x1 square plus mod x2 square, this particular one, this is given a name. It's sometimes written as x and little l2. Why this fancy name for such a simple concept from Pythagoras, motivated by Pythagoras theorem? What does the 2 stand for? I'll recall that in a moment. So you can also define, for example, in Rn, the L1 norm, which is simply mod Vi, as opposed to square root of mod V1 square plus mod V2 square, etc. Okay, this is, why is it called 1? Because there's a 1 here. More generally, the LP norm, where p is larger than or equal to 1, is the pth root, right, of v raised to p. So when p is 2, you get this. When p is 1, you get this. This is sometimes also called the taxi cab norm. For example, if you're in, say, New York City, or say in Bangalore and Malleshwaram or some such thing, you have these roads and you have these crossroads, right? So if a taxi goes from one place to another, the distance it travels is precisely measured using this, right? From here to here it's some distance, and from here to here it's some other distance, and so on and so forth. Okay. Right. Now this, I mean, you also have the L infinity norm, that's defined to be the maximum of mod Vi over all I. That is, for instance, the L infinity norm of, let's say, this vector is the maximum of the numbers, let's say, minus e, mod 2, mod pi, and mod minus e, which is the maximum of the numbers 2, pi, and e, and this is pi, right? Now the point is, you can ask, are these norms secretly arising out of some non-standard from unusual inner products? That is, for example, is this v comma v for some inner product? So the answer here is no. Not all norms arise out of inner products, certainly not these. The only one that arises out of an inner product is this one. Okay. Why is that so? We won't bother getting into that. But more crucially, two norms on any vector space, finite dimensional or not, are said to be equivalent to each other, if there exists constant small c and capital C positive, such that for all vectors the second norm is less than the first norm, which is less than capital C times the second norm. In other words, the lengths are comparable, right? They're not equal to each other, they're not even proportional to each other, but they're not too different from each other, right? Now, this is an exercise, if you will. You must know this as a fact. Any two norms on a finite dimensional vector space, real or complex, are equivalent to each other. Why do we care about other norms? What's the point of norms? Well, we'll see that later on. See, very roughly speaking, we are going to deal with multivariable calculus, right? So, in one variable calculus, we have the notion of the derivative of a function. If the derivative, the magnitude of the derivative mod of f dash is large, that means the function changes very quickly. In multivariable calculus, also we'll end up having a derivative of a function, but it's a more complicated object. It will turn out to be a matrix. So we need to measure how large a matrix is in some sense, right? So that's the point of defining norms. They tell you how large a vector is. But I just said that we have to talk about how large a matrix is as opposed to how large a vector is. Well, here is the next topic. That is, so if you take a matrices, let's say n by n matrices with say real or complex coefficients, complex entries, yeah. So suppose you take matrices. Notice that these are vector spaces. This is an R vector space and this is a C vector space. Why do matrices form vector spaces? Well, you can add. What is a matrix after all, right? Matrix is just a bunch of numbers. You can add two matrices. You can multiply a matrix by a scalar, and addition and multiplication behave very well. Secretly, this is exactly the same vector space as Rn square. This is exactly the same vector space as Cn square. By the way, what does it mean for two vector spaces to be the same? Recall that we have a notion of a linear map between two vector spaces. V is said to be isomorphic. That's the more fancy mathematical word. If there exists a linear map T which is invertible and the inverse is also linear. This, by the way, is a redundant condition. If it's invertible, automatically the inverse will be linear, as you can try to prove on your own, but nonetheless, okay. So in general, two objects in mathematics are the same if you can define a sort of a map between the two respecting the structure of these objects, which is invertible and such that the inverse also respects the structure. Okay. So in fact, these two vector spaces are actually isomorphic. They are exactly one and the same. Why? Because what does addition mean in Rn square? Addition component wise, which is exactly what you do for matrices, likewise for scalar multiplication, right? So you can talk about norms on the space of all matrices. This is a perfectly sensible concept because matrices form a vector space, right? Now, matrices form a finite dimensional vector space, so any two norms are equivalent to each other, but we need two important such examples of norms on the space of matrices. Let's say square matrices, although that's not strictly essential. You can take even m by n matrices. Okay, actually might as well take m by n matrices. Okay. In fact, even m by n matrices form a vector space. R or C, they also form vector spaces. Yeah. This is the same as Rmn. This is the same as Cmn. Yeah. So the first such example is the so-called operator norm. So what's the operator norm? It's an m by n matrix. This is the maximum over all x, so L2. So these are matrices. L2 equals 1 of norm of AX in L2. What does this mean? What does this mean? So what this is it's also equal to the maximum over all non-zero vectors of this. So what is this? More concretely, it's the maximum over x2 square so on equals 1 of, what is AX? The first entry of AX is A1I xi sum over I square. What's the mod square? What's the second entry of AX? A2I xi mod square, and so on. So in its full glory, this is the definition of the operator norm. Why is this a norm in the first place? Well, that's an exercise. Okay, please think about why this is a norm in the first place, right? Okay, it's one thing to define something. You can sit on an armchair and define things all day long, but how do you actually calculate it, right? So we will when we'll talk about diagonalizable matrices, then we'll see how to calculate this. But for now, let's look at another example of a norm. That's the Frobenius, or sometimes called the Hilbert-Schmidt norm. These are very fancy names for a very simple concept, so don't worry about the names. They are not important. So this is a very simple concept. It's simply sum over I and j of mod of aij square. Basically, if you think of Rmn as your space of m by n real matrices, or if you are dealing with complex matrices, then Cmn, complex matrices. Notice that this has an obvious norm already, right? The usual Pythagoras theorem 1. That's exactly this. This is precisely this norm, and likewise this is also precisely this norm, the one coming from the usual norm on these vector spaces. You just square the entries, add them up, and take the square root, right? Right. You can also write it in a very nice way. This is simply the trace of A transpose A. What is the trace of a matrix? Recall, it's simply the sum of the diagonal entries, right? Why is this the trace of A transpose A? Again, please think about this. Yeah. It is crucial to note this property of both of these norms. Both of these examples satisfy this property. Norm of AB is less than norm A times norm B. This is the crucial point. Look, matrices form a vector space, so you can put whatever norm you want on them, they're all equivalent. But what we want is a norm that respects matrix multiplication in this precise sense. A matrix norm is a norm on the space of matrices such that it respects this property. Let's say we are dealing with square matrices. But even if we are not dealing with square matrices, both of these examples satisfy this property, even for m by n matrices, as long as this is m by n and this is n by p. Okay? Both of these make sense for general m by n matrices. Why is this true, by the way? Please do this as an exercise. Right? This ought to have been covered in your linear algebra course, but this is a very crucial property. Okay? So in particular, if A is invertible, that means A inverse is identity, which means the norm of A times the norm of A inverse is larger than or equal to the norm of identity, which is not equal to 0. Typically, for these two examples, this norm of the identity matrix is 1. Because why? When you do this, all the entries, it's not 1, it's n for one of them. For this one, it's n. It's not 0 for both of them. For this one, it's n. Why? Because all of them, except for the diagonal ones, are 0. The diagonal ones are 1, right? So it's square root of, that is, for the norm of identity square is n, so the norm of identity is square root n, right? Now, likewise, if you take the operator norm, you can compute the norm of the identity. What is this? This is by definition, it's the maximum of identity times x, which is x itself. So the maximum of x norm, given that the x norm has to be 1, so that's equal to 1, right? Okay. So this is about norms. We are out of time, so we'll continue in the next lecture.